This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we're diving into a research paper exploring visual large language models, VLLMs. The paper provides a comprehensive overview of VLM applications, challenges, and future directions. Let's start with the core concept. What fundamentally distinguishes VLMs from earlier vision language models, VLMs?
The key difference lies in the integration of large language models, LLMs. Conventional VLMs, prevalent before 2018, used encoder-decoder architectures with CNNs for visual feature extraction and RNNs or LSTMs for text generation. They were task-specific and lacked strong reasoning capabilities. Emerging VLMs 2018-2022 leveraged pre-trained models like Beat and Clip, improving performance but still remaining largely discriminative and limited in multitask abilities. VLMs emerging from 2022 onwards integrate LLMs as decoders, inheriting their generative, instruction following, and strong reasoning capabilities. This allows for generalized and specialized applications across various vision and language modalities.
The paper categorizes VLLM applications into three main aspects: vision to text, vision to action, and text to vision. Let's focus on vision to text. What are some of the key advancements and challenges in this area?
Vision-to-text applications, such as image captioning and visual question answering, VQA, have seen significant improvements with the advent of VLLMs. Instruction tuning, where models are trained to follow diverse instructions, has been a game-changer. However, challenges remain in handling complex reasoning, particularly in specialized domains like remote sensing and medicine. The need for large, high-quality datasets tailored to specific domains is also a significant hurdle. Furthermore, accurately handling high-resolution images and mitigating hallucination, generating factually incorrect information, are ongoing challenges.
The paper mentions several specific vision-to-text applications, including referring expression comprehension, REC, and referring expression segmentation, RES. Can you elaborate on the techniques used to improve performance in these tasks?
RE and RES involve grounding language descriptions to specific regions or objects within an image. Many approaches leverage the LLM's ability to generate coordinates or masks directly. However, some methods integrate specialized modules like the Segment Anything model, SAM, or grounding Dino to enhance accuracy, particularly for complex queries. The trend is towards incorporating more fine-grained visual information and developing more robust training datasets. The integration of multiple image encoders and joint mixing strategies also improves performance in fine-grained tasks.
Optical character recognition, OCR, is another important application. How have VLMs advanced OCR capabilities?
VLLMs have significantly improved OCR by enabling more natural interaction with text-rich documents. Models are trained on datasets of text-rich images, and techniques like shape-adaptive cropping and frequency domain processing allow for efficient handling of high-resolution inputs. Furthermore, mechanisms like shifted window attention and token resampling enhance the model's ability to capture relevant visual and textual information, leading to improved accuracy and efficiency.
Let's shift to vision to action applications. The paper highlights autonomous driving and embodied AI as key areas. What are the unique challenges and opportunities presented by these applications?
In autonomous driving, VLLMs are used for perception, understanding the scene, planning, generating driving maneuvers, and prediction, forecasting the actions of other vehicles. The challenges include handling complex, dynamic environments and ensuring safety and reliability. Embodied AI involves using VLMs to control robots, requiring capabilities in perception, manipulation, planning, and navigation. The key challenges here are in achieving robust perception in 3D environments, learning generalizable manipulation skills, and developing efficient planning algorithms. The opportunities lie in creating more intelligent and adaptable autonomous systems and robots.
The paper also discusses text-to-vision applications, focusing on text-to-image, text-to-3D, and text-to-video generation. What are the key techniques driving advancements in these areas?
Text-to-vision applications leverage the generative capabilities of LLMs to create novel visual content. In text-to-image generation, techniques like optimizing prompts, using sophisticated visual tokenizers, and multimodal fusion are crucial. Text-to-3D generation involves translating textual descriptions into 3D models and environments, often using LLMs to interpret instructions and guide procedural generation. Text-to-video generation aims to create video sequences from textual narratives, utilizing LLMs for scene planning and diffusion models for frame animation. Challenges include ensuring realism, coherence, and efficiency.
The paper concludes by addressing ethical considerations, challenges, and future work. What are some of the most pressing ethical concerns surrounding VLMs?
Ethical concerns include the potential impact on labor markets due to automation, the presence of biases in training data leading to unfair or discriminatory outcomes, and the potential for misuse in applications involving sensitive data. Addressing these issues requires careful consideration of data collection, model training, and deployment strategies.
Beyond ethical concerns, what are some of the major technical challenges that need to be addressed to advance VLM research?
Key technical challenges include improving efficiency, both training and inference, enhancing interpretability and explainability, mitigating hallucination, and improving spatial understanding. These challenges require advancements in model architectures, training techniques, and evaluation metrics.
The paper outlines several promising directions for future research. Can you highlight some of the most important ones?
Future work should focus on improving the security and privacy of VLMs, particularly in applications involving sensitive visual data. This includes developing advanced data anonymization techniques, enhancing robustness against adversarial attacks, and establishing regulatory frameworks for compliance. Further research is also needed to improve the efficiency of VLMs through techniques like token reduction, data distillation, and parameter-efficient fine-tuning. Improving interpretability and explainability is crucial for building trust and ensuring fairness. Finally, enhancing complex reasoning capabilities and exploring new applications in domains like face recognition, anomaly detection, and gaming are important areas for future exploration.
The paper mentions a significant cost associated with training some VLMs. What are some strategies being explored to reduce this cost?
The high cost of training stems from the massive computational resources required. Strategies to reduce this include token reduction techniques that minimize redundant visual information, data distillation methods that create smaller, more efficient training datasets, and parameter-efficient fine-tuning methods that adapt pre-trained models to downstream tasks without retraining the entire model. Research in these areas is crucial for making VLM technology more accessible and sustainable.
The discussion of hallucination in VLMs is particularly relevant. What are the root causes of this issue, and what are some effective mitigation strategies?
Hallucination, the generation of factually incorrect or irrelevant information, arises from several factors: misinterpretations by vision encoders, complex or ambiguous visual inputs, biases in training data, and adversarial attacks. Mitigation strategies include improving the quality and diversity of training data, enhancing cross-modal attention mechanisms using constrained decoding, and incorporating factual verification steps during generation.
The paper touches upon the importance of spatial understanding in VLMs, especially for embodied AI and autonomous driving. How can we improve the spatial reasoning capabilities of these models?
Improving spatial understanding requires enhancing the model's ability to identify spatial relationships between objects and perform egocentric allocentric transformations. Techniques like chain of thought, COT prompting, tree of thought, TOT reasoning, and visual prompting can help. Furthermore, integrating more robust 3D scene representations and developing specialized training datasets focused on spatial reasoning are crucial.
Finally, the paper briefly mentions other potential applications of VLMs, such as face recognition and anomaly detection. What are the unique challenges and opportunities in these areas?
In face recognition, challenges include privacy concerns and the limited availability of instruction-based datasets. Opportunities lie in developing more accurate and robust facial analysis systems. In anomaly detection, challenges include data distribution bias and interpretability. Opportunities exist in creating more effective systems for detecting anomalies in various types of visual data. In both areas, the integration of domain-specific knowledge and tailored training strategies is crucial.
This has been a thorough discussion of the paper's key findings. Thank you for your insights.